Hello all, hope you're doing well today. Today we are talking about the responses and adaptations to aerobic endurance training. This is chapter 6. So in this chapter, really, you should be able to identify acute and physiological responses to aerobic exercise as well as the chronic adaptations. Understand the factors that influence adaptations to aerobic endurance training, and identify and understand the physiological factors associated with overtraining, as well as with detraining. So here we go. Acute responses and chronic adaptations are two different types of physiological changes that occur in response to exercise or physical activity. Acute responses refer to the immediate physiological changes that occur during or shortly after a single bout of exercise. These responses are temporary and typically return to baseline levels once the exercise session ends. Chronic adaptations, on the other hand, refer to the long-term physiological changes that occur in response to regular exercise training. These adaptations are specific to the type, duration, and intensity of exercise and can have a significant impact on overall health, fitness, and performance. Acute responses to aerobic endurance exercise, also known as cardiovascular aerobic exercise, are the immediate physiological changes that occur during or shortly after a single bout of sustained rhythmic activity that engages large muscle groups and elevates heart rate. These responses are important for meeting the increased demands for oxygen and energy during exercise. Here are some common acute responses to aerobic endurance exercise as it relates to cardiovascular response. There's an increased heart rate. As exercise intensity increases, the heart rate rises to pump more oxygenated blood to the working muscles. This helps meet the increased oxygen and nutrient requirements. Each system is dominant under certain conditions. The sympathetic system predominates during emergency fight or flight reactions and during exercise. The overall effect of the sympathetic system under these conditions is to prepare the body for strenuous physical activity. More specifically, the sympathetic nervous system will increase the flow of blood that is well oxygenated and rich in nutrients to the tissues that need it, and particularly the working skeletal muscles. The parasympathetic system predominates during quiet and resting conditions. The overall effect of the parasympathetic system under these conditions is to conserve and store energy and regulate basic body functions such as digestion and urination. You also see an increase in stroke volume. With stroke volume, it refers to the amount of blood ejected from the heart with each contraction. During aerobic exercise, stroke volume increases due to increased ventricular filling, resulting in greater volume of blood being pumped per heartbeat. You also see an increase in cardiac output. Cardiac output is the total amount of blood pumped by the heart per minute. It is calculated by multiplying heart rate by stroke volume. During aerobic exercise, both heart rate and stroke volume increase, leading to a significant rise in cardiac output. And you can see so it's liters per minute, and looking at cardiac output, which is equal to heart rate, beats per minute, and stroke volume, liters per beat. The Frank-Starling law states that the stroke volume of the left ventricle will increase as the left ventricular volume increases due to the myocyte stretch, causing a more forceful systolic contraction. This assumes that other factors remain constant. You also have an increase in vasodilation. The blood vessels, particularly those supplying the working muscles, undergo vasodilation or widening in response to aerobic exercise. This allows for increased blood flow, delivering more oxygen and nutrients to the muscles and facilitating the removal of waste products. Increased respiratory rate. To meet the increased demand for oxygen and remove carbon dioxide generated during exercise, the respiratory rate or breathing rate increases. This is going to enable a greater exchange of gases in the lungs. There's an increase in oxygen uptake. So oxygen uptake is the amount of oxygen consumed and utilized by the body during exercise. It reflects the body's ability to transport and utilize oxygen for energy production. Aerobic endurance exercise results in a substantial increase in oxygen uptake. Following intense aerobic exercise, there is an oxygen debt or excess post-exercise oxygen consumption, or EPOC. This is the amount of oxygen required to restore the body to its pre-exercise state. The increased oxygen consumption during recovery period helps replenish energy stores, clear lactate, and restore other physiological processes. You'll also see with aerobic exercise that it leads to an increase in body temperature. To regulate body heat, the body initiates sweating, which aids in cooling down through evaporation. These acute responses to aerobic endurance exercise are adaptations that occur to meet the increased metabolic demands of working muscles and maintain homeostasis. They support improved cardiovascular function, oxygen transport, and energy production, contributing to enhanced endurance and fitness over time with regular training. During aerobic endurance exercise, there are several acute cardiovascular responses that occur in order to meet the increased oxygen and energy demands of the working muscles. These responses include, number one, a redistribution of blood flow. So during aerobic exercise, blood flow is redistributed within the body. The working muscles receive a higher proportion of the total blood flow, while blood flow to non-essential organs, such as the digestive system, decreases temporarily. Aerobic endurance exercise typically leads to a temporary increase in blood pressure. That's due to the increased cardiac output and peripheral vasoconstriction in non-working muscles and organs. You also see oxygen extraction from the blood by the working muscles increases during aerobic exercise. That's to facilitate the enhanced capillary density and improved oxygen utilization within the muscle tissue. Aerobic exercise promotes venous return, that flow of blood back to the heart through mechanisms such as muscle contractions, respiratory movements, and vasodilation. This facilitates the return of deoxygenated blood to the heart for reoxygenation. You also see with aerobic endurance exercise, the respiratory system undergoes acute responses to support that increased oxygen demand and removal of carbon dioxide generated by the working muscles. And part of that's the increased breathing rate. The primary acute respiratory response to aerobic exercise is an increase in breathing rate, also known as the respiratory rate. This is the number of breaths taken per minute. The increased breathing helps to deliver more oxygen to the lungs and remove carbon dioxide more efficiently. The tidal volume increases as well. That refers to the volume of air inspired and expired with each breath. During aerobic exercise, there is an increase in tidal volume, allowing for a greater exchange of oxygen and carbon dioxide in the lungs. Minute ventilation is increased. It's the total volume of air breathed in and out per minute. It's calculated by multiplying the breathing rate by the tidal volume. During aerobic exercise, both the breathing rate and tidal volume increase, resulting in a higher minute ventilation. This enables a greater supply of oxygen to the body and removal of carbon dioxide. You also have an enhanced oxygen uptake, also known as VO2, which is the volume of oxygen consumed per minute. It increases during aerobic exercise. And that's just a reflection of the body's ability to transport and utilize oxygen to support energy production in the working muscles. Aerobic exercise stimulates a more efficient exchange of respiratory gases in the lungs. Oxygen from the inhaled air is transferred to the bloodstream, while carbon dioxide, a waste product of metabolism, is removed from the bloodstream and exhaled. The muscles involved in respiration, such as the diaphragm and intercostal muscles, are activated to a greater extent during aerobic exercise, allowing for more forceful contractions and increased ventilation. During aerobic exercise, the body produces more carbon dioxide as a result of increased metabolism. It can lead to a temporary decrease in blood pH. To counteract that, the respiratory system responds by increasing ventilation to remove excess carbon dioxide and maintain that acid-base balance. These acute respiratory responses to aerobic endurance exercise facilitates the uptake of oxygen, removal of carbon dioxide, and maintenance of the acid-base balance. They work in conjunction with the cardiovascular system to ensure that the working muscles receive the increasing oxygen necessary and nutrients while efficiently eliminating metabolic waste products. Through regular aerobic training, these acute responses can lead to chronic adaptations in the respiratory system, such as increased lung capacity and improved respiratory efficiency. The respiratory exchange rate, or RER, looks at carbon dioxide production and oxygen uptake, and the increase with the exercise intensity and measured under steady state conditions is commonly used to indirectly determine the relative contribution of carbohydrate and lipids to overall energy expenditure. There are acute metabolic responses that occur to exercise as well. They refer to the immediate changes that occur in the body's metabolic processes during or shortly after physical activity. These responses are aimed at meeting the increased energy demands of the working muscles. Here are some of the key acute metabolic responses to exercise. There is an increase in energy production. Exercise stimulates the metabolic pathways responsible for energy production. The body relies on various fuel sources, including carbohydrates, fats, and to a lesser extent proteins, to generate ATP, the energy currency of the body. There is an increase in oxygen consumption, or VO2. It is a measure of the body's ability to utilize oxygen during exercise. VO2 increases as the body requires more oxygen to support energy production and aerobic metabolism. The Fick principle is a mathematical equation that calculates cardiac output by multiplying the difference between arterial and venous oxygen partial pressures by the blood flow through the vascular bed. In other words, it takes into account how much oxygen is being delivered to and from the tissues. It makes it a more accurate measure of cardiac output than simply measuring heart rate or blood pressure. You also see an increase in respiratory exchange rate, which is the ratio of carbon dioxide produced to oxygen consumed during metabolism, and during exercise, the RER increases as the body relies more on carbohydrate metabolism, resulting in a higher ratio of carbon dioxide production. During high intensity exercise, when the oxygen supply cannot meet the demand of the working muscles, lactate is produced as a byproduct of anaerobic glycolysis. Lactate accumulation can contribute to muscle fatigue, but it can also be used as a fuel source during low-intensity exercise. During acute exercise, the endocrine system, which includes various glands that produce and secrete hormones, undergoes several responses to support and regulate physiological processes. These endocrine responses play important roles in modulating metabolism, energy utilization, and overall body homeostasis during exercise. Here's some key endocrine responses to acute exercise. You see an increase in epinephrine and norepinephrine. Exercise stimulates the release of epinephrine, which is adrenaline, and norepinephrine, or noradrenaline, from the adrenal glands and sympathetic nerve endings. These hormones act as catecholamines and play a crucial role in increasing heart rate, blood pressure, and mobilizing energy stores by promoting glycogen breakdown and fat oxidation. There's an increase in cortisol, which is known as the stress hormone, and is released from the adrenal glands in response to exercise. Its levels rise during exercise, especially during prolonged or high-intensity activities. Cortisol helps mobilize energy reserves by promoting protein breakdown, gluconeogenesis, the production of glucose from non-carbohydrate sources, and the release of fatty acids. There is an increase in growth hormone. This exercise triggers the release of growth hormone from the pituitary gland. Growth hormone stimulates protein synthesis and promotes fat oxidation and helps regulate blood glucose levels. It also plays a role in tissue repair and recovery. There's an increase in insulin, temporarily in insulin secretion. Insulin promotes glucose uptake by the muscles and facilitates the storage of glucose as glycogen. During intense exercise, the increase in insulin is typically modest compared to the increase in catecholamines, allowing for the availability of glucose as an energy source. There's also an increase in glucagon, which is produced by the pancreas. It is released in response to low blood glucose levels during exercise, and it acts in opposition to insulin by promoting the breakdown of glycogen into glucose. through glycogenolysis and the production of glucose from non-carbohydrate sources, or gluconeogenesis. There is an increase in testosterone in both male and females. Acute exercise can temporarily elevate testosterone levels. Testosterone plays a role in muscle protein synthesis, muscle growth, and recovery. The increase in testosterone can enhance protein synthesis and aid in adaptations to exercise. Exercise stimulates the release of endorphins, which are endogenous opioids that act as painkillers and mood enhancers. Endorphins contribute to the feeling of euphoria and reduced perception of pain during and after exercise. Acute exercise can also lead to an increased secretion of thyroid hormones, including thyroxine, T4, and triethylthionine, or T3. These hormones regulate metabolism by increasing oxygen consumption and energy expenditure, as well as heat production. These endocrine responses to acute exercise play an important role in regulating energy metabolism, mobilizing energy stores, maintaining blood glucose levels, and promoting tissue repair and adaptation. The magnitude and duration of these responses depend on factors such as exercise intensity, duration, and individual fitness level. Regular exercise training can lead to adaptations in the endocrine system, resulting in improved metabolic efficiency and overall fitness. So we've talked about the acute responses of aerobic exercise here today. We will talk about the chronic adaptations in our next session. I'll talk with you soon. Have a great day.